Hello everyone. In this lecture, we are going to see about the temperature distribution when a heat conduction is occurring through a wall. I can give you a simple example of heat conduction through the walls of your house during the winter season. You imagine you have four walls in your room, and during the winter season, most of the heat is being lost away from inside of the room to outside. You agree with that? So this is happening because of the temperature difference that is existing inside the room as well as outside the room, right? So whenever there is a temperature gradient, definitely there will be a heat transfer occurring in that direction alone, right? And always a heat transfer will occur in an area which is normal to the area of the wall, that is perpendicular direction, right? So we can neglect the sites which doesn't have a temperature gradient, or um, the other areas, that is the areas which are not perpendicular to the wall. So keeping this as the base, just directly moving on to the derivation of temperature distribution. So the temperature distribution in a plane wall, right? Now let me take a wall which is having a thickness 0 to L. Let this extend in the x direction. The temperature on this side of the wall, let it be T1, and this side, let it be T2. Let this be at a higher temperature and this at a lower temperature. So I can show a temperature gradient by this line, right? We have already seen the general equation, that is d square T by dx square is equal to 0. This is for a steady state and without any heat generation. Now let me integrate this equation twice. I will get dt by dx will be equal to a constant. Then integrating further, C1x plus C2, where C1 and C2 are simple constants, right? Now applying the boundary conditions. What are my boundary conditions? At x is equal to 0, my wall temperature will be equal to T1. At x equal to L, the wall temperature is equal to T2, right? So I am applying these two boundary conditions in this equation. Okay. Now let me apply the first one. T will be equal to T1. What about this x? This term will vanish away. So I will get C2. Applying the second boundary condition, T will be equal to T2 and C1 I don't know. What about x? It will become L plus C2. I have already written as T1. Right? Now finding out the value of C1 is going to be T2 minus T1 divided by L. Right? Therefore, temperature at any distance x will be equal to, we have already seen, what is that? C1x plus C2. C1 is this value and C2 is this value, right? So it is T2 minus T1 by L into X plus C2 is actually T1, right? So this is the temperature distribution equation for a plane wall. Okay. Now we are going to see two other terms, that is thermal resistance and thermal resistance network. Okay. Once you understand what is thermal resistance, then the network is very easy. Thermal resistance. I'm taking this example, the same wall that we have seen. This is T1 and here it is T2, from high temperature to low temperature. Okay. Imagine here it is 60 degrees Celsius, just for example. And this is 40 degrees Celsius. So because of the existing temperature gradient, there will be a heat flow from T1 to T2. Okay. So I can write this as Q equals T1 minus T2 divided by R. This R is called as thermal resistance. What is meant by thermal resistance? That is, the air or any other medium that is present here will definitely offer a resistance to the heat flow. In electric circuits, we have studied about in the passage of current, there will be a resistance V equals IR. You remember this, right? So this is the electrical resistance. Similar to that, here we have thermal resistance. So this resistance is offered with respect to the temperature. Okay. So this is some sort of opposing force. Now we can explain this thermal resistance as L by Ka. L by Ka. Now what is this? We know it is a, I'm sorry. We know this L. This is actually the thickness of the plane wall. K is the thermal conductivity and A is the area that is perpendicular to the heat transfer across the walls. Right. Now you have taken just a plain wall where T1 and T2 are present. What if there are convections on either sides of the walls? In such case, I'm taking the same wall, see here. This is T1 and T2. Now this is exposed to an ambient condition T alpha 2 here. This is T2 here, T1 here, and this is T alpha 1 here. Okay. So what does this mean? There is a convection on the left side of the wall as well as on the right side of the wall. Now I can show the resistance existing here, another resistance here, and another resistance here. So this is called as wall resistance. This is called as convection resistance. And this is also convection resistance. What will be the temperatures at the nodes? This is T1, this is T2, and this node is T alpha 2. Okay, now is the circuit clear? For this condition, if we are going to calculate the total resistance, then R total will be equal to 1 by H1A. Okay, where H represents heat transfer coefficient. H1A is on the left hand side of the wall, that is T1 wall, plus L by Ka. This is the wall resistance, and this is 1 by H2A. Again, it is a convection resistance. So here the medium will have a value of H2, and this side the medium will be having a value of H1. Okay. Now, UA, that is overall heat transfer coefficient into A, will be equal to 1 by R total. Clear? So Q will be equal to UA into delta T. Whenever you come across circuits or networks where you have more than one resistance, that is, you have a convection resistance as well as a convection resistance, or even in case of radiation, you have radiation resistance. So when you have too many resistances, they form a network, and you will have to calculate the total resistance and then find out the universal heat transfer coefficient, right? So this will be universal heat transfer coefficient. Next, you have something called as thermal contact resistance. Now this comes into action when you have two different materials. Okay, suppose I'm having a wall like this. In addition to that, I have one more wall. Okay, let me show the thickness as different. So that's why I made this one thick compared to the other one. Okay, now this is an example of multi-layer solids. Right? So when you actually observe through a microscope, you will understand that this contact surface is not so even. In other words, when you zoom like this, right? Okay, your surface will be like this, some sort of irregularity, and you can see the voids. Okay, so this gaps which is filled by air or some other medium. So this medium will actually have a very poor conductivity, and therefore it will prevent the heat transfer. So that term which is referring to this is called as thermal contact resistance. It is represented by RC. C stands for contact. So that is equal to L by K. Okay, L is the length. This is L. K is the thermal conductivity of this material. Okay, this is called as thermal contact resistance. Now that's all. So what we have seen in today's lecture is how to find out the temperature distribution in a plane wall. We have taken the simplified heat conduction equation, that is dou square T by dou x square, and then we have integrated it twice to find out the constants. So C1 and C2 are determined. Then we have applied the boundary condition. Boundary condition is again from the same figure itself. That is x equal to 0, temperature will be T1. X equal to L, the temperature will be T2, right? Then finding out the value of C1 and C2. Here we have the temperature distribution equation. So whatever value of x, imagine the wall is of thickness 50 mm and you want to find it out at 20 mm, your x will take the value of 20 and L will take the value of 50. Okay. Then we saw what is thermal resistance. So some resistance that is offered to in the direction of heat flow. Okay. Due to temperature gradient, there exists a heat flow, but because of this the thermal resistance and heat flow is considerably reduced. So that term is called as R. And R is defined as L by Ka, where you know what is K, that is thermal conductivity, and A is the area. Suppose there are too many resistances, there can be conduction resistance, convection resistance, or even thermal contact resistance that is due to air gaps. So in such case, you can consolidate all these resistances and find out what is UA. This UA is substituted in the heat transfer equation. So Q equals UA delta T. That is universal heat transfer coefficient. A is the area and delta T is the temperature difference. And this we have thermal contact resistance. This always exists due to two different solids that are being arranged parallelly. Okay. So multi-layered solids which will have different properties. That is K value is different. L value is also different. So because and at the place of joining, though they look so smooth, they're actually not so smooth. Uh, there will be some irregular voids, and that voids is being filled by some mediums like air, which will have very low thermal conductivity. Okay. So that is all for today's lecture. Thank you for watching. Any doubts, please feel free to post in the comments. Thank you.